Hey folks, Ms. Gosling here. In this video, you are going to learn about how circuits act in labs. By the end of the video, you will be able to construct potential divider circuits and describe the causes of experimental uncertainty in an electronics lab. So let's go ahead and get started, shall we? So on the left here, I have an image of a potential divider circuit. Now, in a potential divider circuit, you can tell in the name, we are dividing the electric potential. So the simplest way to do this is to simply have two resistors and put a second circuit or measure our voltage across our second resistor. So why on earth is this useful? I mean, it's basically just a series circuit, right? Well, it's useful for a number of reasons. First, it's a good way to include temperature-dependent components in a circuit. So, for example, if you want your refrigerator to send out a sound when it's not working, so to beep when the door's left open, for example, what you can do is you can put something like a thermistor here where we have R2. And the thermistor is going to have a resistance that is highly dependent on its temperature. So, as it warms up, its resistance will change, and depending on the way you have your circuit set up, that could, for example, cause a sound to go off. So that's one reason why we might want a potential divider circuit. I also might use this circuit if, for example, I have only one battery in my lab, and I'm trying to get a voltage, say my battery has a voltage of 6 volts, and I only want a circuit with 3 volts. What I can do is I can make sure that these two resistors are equal, and then I can put in a third resistor here across that voltage divide. And since 3 volts are lost across my first resistor, there's only going to be 3 volts traveling through my new load resistor. So it's something that I can use when I'm limited in my materials. So it gives me more variety in circuits in a lab. So if I needed to have 5 levels of my IV, but I only had one battery, if my IV is voltage and I only have one battery, this is one way that I can get multiple levels of the IV without having to go out and buy a bunch of other batteries. So another example of a use of a potential divider circuit is using a tool called a rheostat, which I have drawn in here. And with a rheostat, essentially what I can do is I can plug the rheostat into my voltage of a fixed voltage, and I can attach a resistor that has a fixed value. And as I move where the attachment of my fixed resistor is, I'm actually changing the voltage through the resistor. So for example, if I were to take my connection and move it to the top, I might have a voltage drop of 2 volts, assuming that that's the total voltage in my battery. If I were to move it, however, to the edge here, all my voltage would be lost before reaching my battery. Here, let me redraw this a little bit nicer. So say that I attach this connection here, all that voltage is lost before we even reach my fixed resistor. And so the voltage drop across my fixed resistor will be 0 volts. Similarly, I could attach this somewhere perhaps to the middle, and the voltage drop that I would get would be approximately 1 volt. So the use of a rheostat is it gives me a much wider range of voltages that I can look at, because rather than being stuck with using the resistances that a variable resistor has built into it, I can change it with very, very incremental values, giving me a wider range of experimental data, which, as we know, is very useful in the lab. So, speaking of labs, I do want to take a moment to talk about some of the sources of error in electrical labs. And the first thing I want to talk about is a zero error. So, say I have an ammeter that is not attached to anything. So it's just got its two leads hanging out, unattached to anything. And yet, on its screen, it says it's reading a current of 0.1 amps. What that means is that my ammeter has a 0 error, meaning that when it should be reading 0, what it's reading is 0.1. As a result, all of my experimental data is going to have a value increased by 0.1 amps. So say that the current that is actually running through my circuit is 1.0 amps. What my ammeter will read is 1.1 amps. What's really nice about a 0 error, though, is that it's systematic, and so you're going to have the same error in every single data point, and so as a result, it shouldn't really affect your analysis in a meaningful way. The next thing is something that's very important to keep in mind if we're looking at a battery over a long period of time. So the thing about batteries is that they tend to lose voltage over time, and as a result, the voltage reading on the battery is not always accurate. So you may look at your battery, and it may say that it's a 9-volt cell, but when you hook it up to your voltmeter reads it as being, say, 8.8 volts. As a result, all of the data in your experiment is going to be affected by that. So you may be expecting to have, so say we know that V equals IR. Say that I'm plotting voltage versus resistance and using that to measure current. If my cell has a voltage of 8.8 volts instead of 9, that is of course going to affect my data point there. Again, this could be a systematic error. It could also be a random error if you're using a bunch of different cells, or if the cell that you're using is losing its potential over time, because that does happen. So a way to deal with this error in the lab, guys, is to actually measure your voltage of your cell before using it in your circuit. And when you do that, what you'll be able to catch is what its actual voltage is rather than theoretical voltage that's listed on the battery. And finally, the last thing is the hardest to combat because we really can't do anything about it. So the last source of error in electrical labs is the resistance in wires and meters. So when we look at a circuit like this in a problem, we often assume that the resistance of the wires is 0. Similarly, we would assume that if we put a voltmeter in our circuit, or if we put an ammeter in our circuit, that those would also both have resistances of 0. However, we know for a fact that that's not the case. There are no magic wires or magic meters that are fully free of resistance. So as a result, having measuring components and wires in your circuit is going to increase your error. So one thing you can do is try to reduce the amount of wire you're using. So I can build a circuit with really long wires or really short ones. And given the choice, I'm going to want to make my circuit's wires as short as possible in order to reduce any of the voltage that's lost in those wires. Meters are a little more difficult to change the error in, to decrease the error in. However, one thing that we can do that is helpful actually is to use a potential divider circuit, because that lowers the total voltage over our component. It lowers the current through the circuit, and as a result, it is going to lower the loss of energy due to heat in the circuit, in the wires, and in all the components of the circuit, which is a really helpful way to reduce our error due to wires and due to meters. Okay guys, so let's talk takeaways. First of all, potential dividers help us increase the range of available voltages and decrease experimental error. Secondly, there are many sources of experimental error in circuits, and it's really important to be aware of what they are and how you can reduce them. So guys, hopefully you have learned something here. This should be something that will be helpful for you when you're writing the conclusion to a lab in a circuit lab. Or if you're doing a circuits IA, these are things you're going to want to keep in mind. Anywho, I'm going to go ahead and let you all go. Best of luck and happy solving.